I also have a question.
I know that someone is speaking. Could you please repeat it?
I have a question about changing the fixed um,
The direction.
a part a fixed connection in.
Okay, let's do like we can go straight on the if this question is related to this particular exercise. Okay. Otherwise, we can go on, and then I will reply to all the specific questions during the break.
In this particular exercise, we changed the fixed connection in the part A to a hinge, I believe, for continuing to solving the exercise, and I didn't understand why we did that.
Okay, sorry, but I just lost the audio a lot of times. Could you please repeat the question? If it is related to this exercise. Now I'm not listening anything.
He's placing his question in the chat, I guess.
Is it in the chat?
Yeah, he wrote it there.
Okay. We're changing the fixed connection in A. Okay, basically, now what's happening? Whether it's the audio. Just a second. Okay, so basically we just downgrade, similarly to what we did in the node C, we just downgrade the, how is that help us in solving the problem? Okay, the point in the logic of the force method is we start from a static redundant structure, but it works also for static determined structures. If we have a static redundant structure, we cannot solve this structure using only equilibrium equations. Okay, this was explained during the last last lecture, because if we exploit equilibrium equation, we can find only a number of unknowns, which are the external forces, that is equal to the number of equilibrium equation we can write for the structure. How many equilibrium equations can we write? We can write one equilibrium equation per each degrees of freedom of the structure. In this case, we have just one structure, one element, because the structure is continuous from A straight to D, so we can write just 3 equations of equilibrium. Okay, and we can decide whatever equilibrium of equation we can write. In this case, we have too many unknowns, too many restraints, so we cannot find the values of all the external reactions using only the 3 equilibrium equations that we can write, because we have more restraints than degrees of restraint, degrees of freedom. So we need something more. What do we need? We can use compatibility equations. That's what the force method is based on. And this was basically the theme of the lecture of Gentile last week. Now we are just reviewing it, trying to understand how to apply this force method. The logic is we do not work on the original structure because it is statically redundant. So we cannot solve it using equilibrium equation. We create a second structure which is statically determined. Okay, so we have an equal number of degrees of restraint and degrees of freedom. So we can solve this structure using equilibrium equation. But we have 2 unknowns. We have one unknown x1, which is the first degree of restraint that we have released, and then we have x2, that is the second redundant force that we have that is associated to another restraint that we have released. So we release some restraints, we get a structural, statically determined structure, something that we can solve using the equilibrium equation, but we are adding two unknowns in this case. How can we find the values of these unknowns? Simply, we write the equation, and that's what I'm going to do right now. And I will try to do this. What's happened? Okay, good news. Okay, I do not have to click that.
Sorry, can I ask just one thing? Sorry.
So, no, okay, I will not
hear me?
Because it's too long.
Do you hear me?
Guys, it is... there is a question?
Yes, sorry. I was just
Yep.
I just wanted to ask you if we have to decide which one to release. I mean, the structure is just
absolutely.
Okay.
To decide whatever you want to release.
Because it's just one time redundant, right?
Yeah. You can also decide
sorry.
to keep the structure like this.
Okay.
So that you have just a clamped-in section. The beam is continuous, and then you have a force here and a force here. And then, okay. The horizontal forces are not important because we can get rid of them because we have no forces applied. But that structure is way more complex to solve than this, and the reason is that if we stick on structures like simply supported beams with generic length, we can use the flexibility coefficient that were explained by, we can find them using the elastic line or the principle of virtual works or whatever other method. The logic is that now we are just saying that the rotation in the node A has to be equal to something. You know what has to be equal to rotation in the node A, such that this structure, this one, is equal to the first one. Because we all agree that this structure is different from this one. Okay? But we have to solve the second one in order to find the solution that are the same than the first structure. So we have to impose some compatibility equation, and the first compatibility equation is there is someone in the lobby. Just a second. Okay, no one is replying. I hope that you are just shy, because every time we downgrade, how can I add there? Okay. Now you're in. Every time we downgrade one exercise, one restraint, we have to impose the original motion. In this case, the section A was fixed. Okay, so we had no displacement and no rotation. We have released this possibility, allowing this node to rotate. Okay, but we have to impose that the rotation in node A has to be equal to 0. So we can find those values of x1 and x2 such that the rotation in A is restored equal to 0, so that this structure, the second one, is equal to the first one. This is the first compatibility equation, and the second one is that rotation. What's happening? Okay, the rotation. Okay, no, let's say that the difference of rotation in the node B is equal to 0. Okay? So that in the node, no, not in the node B, sorry, that was a mistake. It is in the node C. Okay, before I forget, I want to decide 1 hour per week where I will be online on my personal page, and you know the address. And so whoever wants to ask questions about the theory or the exercise can connect at that hour and meet me, okay? Even without writing mails. And if I'm not present, you can write me an email so that I will access. And I will say the date during the last part of the lecture. So hope it helps. Then, okay, so we have these two compatibility equations which associated to this structure help us to recreate the original one. So let's write again the structure. And now we can use the superposition principle. Then we have a force QL. Given the moment here, x1, x2 is applied in the node C. Well, we apply the superposition principle. So we solve the first structure only applying the external load QL applied in the mid-span. Okay, so this is the first structure. What do we need to find? The rotation in C. Where is it? Not here. Here. We have to find the rotation associated to the node A and the difference of rotation between the left-hand side and the right-hand side in the node C associated to QL, because the values of x1 and x2, the actual values of x1 and x2 will be the two values that associated to this geometry and this external load will allow us to have 0 rotation in the node 1 and 0 mutual rotation in the node C. So we write the deformed shape associated to this load. We all agree that if we have a beam, the deformed shape associated to this load will be something like that. We have possibility to rotate in the node 1 and possibility to rotate in the node C. So we want to know how much is CA0, and then this angle C0. Okay? This angle is also the difference of rotation in the node C, because we have a deformation of this beam in the node C, a mutual rotation of AC with respect to CD equal to this angle. Okay, so phi A1, okay, we have to know how much is phi A1. We know we can refer to reference examples, and in this case are all simply supported beams. If you look for flexibility coefficients for the fourth method online, you will find the tables and tables. We can also send them by mail to you, some specific ones, associated to generic load condition. In this case, if we have a generic load Q applied on a beam with length 0, we know, we can find that the rotation associated at each of the nodes, in this case we have a generic node 1 and a generic node 2, P1 will be equal to, okay, let's look for it. It is Q, the value of the load applied in the midspan, times the length of the beam to the power of 2 over 16, yes, 16 times iota, times E, which is the Young's modulus of the beam, iota. And we have already discussed the meaning of all these stuff. In this case, phi A0 will be equal to, someone wants to say how much is phi A0 associated to a load QL on this beam? Someone wants to guess? Nobody? Okay, this, I will say this. Okay, I will go on. The load is not Q, capital Q, but is Q times L. This is a Q. Q times L. Times the length of the beam to the power of 2. In this case, the length of the beam 2L. Here I have not replied it, but we can remember if you look for your exercises. Q to the power of 2 over 16 E iota. This is also delta phi C0 because the structure is symmetric and the rotation in the first node is equal to the rotation in the second node. It is the same. Okay. So we have found the first influence coefficients for the first structure. Then we can recover. Now what do we have to do? We have to consider the influence of x1. So we will find the values of the rotation in node A and in node C associated to a load x1. So we write again the structure.
Sorry.
Yep.
I have one question because the length was L plus L, so should be 2L or not?
No, sorry, could you please, oh, no, wait. I cannot really, just 1 second. I need to do something. Okay, could you please repeat the question?
The length between A and C was L plus L, right?
Yeah, I remember too. It was 12, I think.
Okay, just 1 second. I will try. Okay, can you, sorry, repeat the question? No, maybe I should be able to hear it.
I was talking about the length between A and C.
Yes, this is the original, sorry, this is the original structure, the first plot I was drawing, and you can see that between A and C there is 2L of length, because we have L from A to B, and from B to C we have another L.
Yes, so at the end the result is 2L.
Yep, absolutely. In fact, 2L. In fact, in this case, in the generic case where we have a simple supported beam with a generic load Q and length L0, I am saying it, I'm calling it L0 in order to say something completely different from what you've seen. I'm not calling it L. So the rotation in the node 1 is the value of the force applied in the midspan times the length L0 to the power of 2 over 16 e iota. Okay. So if we, no, okay. I said it, but I didn't write it. You are completely right. You are saying this, right?
Yes. Yes.
This is a 2. You have to use your imagination. Yes, thank you. Because I said it, but I didn't write it. Okay, perfect. So we can go on. Thank you, ma'am. Now we have this was an inch. Okay. Now we are considering just x1. We have seen many times that the deformation associated to a simply supported beam, a bending moment applied, no, not many times, but the last lecture, we saw that the deformation associated to a simply supported beam, in this case it is the beam AC. I'm asking it, can you hear me properly? Can you hear me well? Because maybe you will hear some kind of echo.
We can hear you well.
Yeah, we can hear.
Okay, thank you. So we have a bending moment applied in the first node of the structure. The deformation associated with this one. We have, in this case, rotation PA1, because it is the one associated to the first static unknown, and it is equal to x1 times L, and in this case, L, as before, it is 2L, because it is the length of the beam, over 3 e iota. Okay? So 2/3 x1 L over iota. Whereas P1, so the difference between the rotation in this node and the rotation in the other part of the structure is just x1 times the length, 2L, over 6 iota. It is 1/2 of the previous one. So we have found also these coefficients. They were trivial. if there are no questions, we can move forward to the last case. Please notice that this restraint is qualitatively equal to this. I am drawing the circle on top just to remember that it is an internal hinge that allows possibility to rotate of beam AC with respect to beam CD. Okay, they are both hinges. In this case, we had x2. If I'm not wrong, this was the direction. Yes. So the deformation associated is on the beam AC, we have a moment which is counterclockwise. So we will induce a rotation that is counterclockwise in the node C. And clockwise in the node A. So we have A equal to x2 times 2L, which is the length of the beam AC, over 3 E iota, whereas delta phi T, and this is phi A2 and delta phi C2, is equal to, this is an equal, even if it doesn't seem, x2, changing the color, green, x2, okay, you tell me. We have the rotation in the node, in the beam AC, which is equal to x2 times, anyone wants to guess? Ah, there is a mistake. This is not 3 iota, but it is 6 iota, because it is rotation on the other node, on the second node where the bending moment is not applied, but it is the opposite one. So the rotation C, in the node C, in the first beam is x2 times the length is sine, okay, 2L over 3 iota. Is it the only contribution? Do we have only the right-hand side rotation? Yes, no? Maybe? Please, is somebody listening to me? Okay, I will go on. There is clearly not only this contribution, but there is also the rotation on the other side, because we are saying that the difference of rotation in this beam, in this node of the beam AC with respect to CD. So far, we had only rotation in the node, in the beam AC. But in this case, we have rotation both in the node AC and also in the node CD, because x2 is applied on both beams. So the mutual rotation is not only this one, but is also x2 times the rotation in the CD, which is x2 times L over 3 E iota. It is equal to the previous one, but the length is different. So since we have a smaller beam, which is the beam CD, since the beam is smaller, the rotation associated in this node is 1/2 of the rotation in the node AC. Okay, because smaller is the beam, the stiffer it is. It is intuitive. Okay, so the sum is 3 e iota x2 L 3. 2 plus 1. So it is x2 times L over e iota. Now we have found all the contributions. And what do we need to say? Anyone, please? Otherwise, I'm talking to myself.
We have to add all the components like phi A0 plus phi A1 plus.
Great.
And it has to
Okay,
be
we
equal
have
to
to
0.
restore the compatibility equation. That's right, exactly. Please remember that these kind of questions are possibly the questions that Professor Gentile, or even myself, will ask you during the oral exam, because it is not a resolution of an exercise, but it is just the methodological path. So we originally said that phi A is equal to 0, but phi A, using the superposition principle, is the sum of phi A0 plus phi A1 plus phi A2. We have all these terms equal to 0. So we just go back, we find this is empty, so not this. Okay, the first one was black, Q. I have to see it here. Okay. Q times 4L, this is a 4, over 16 e iota, which is obviously equal to Q times L over 4 e iota, plus phi A1. Phi A1 was equal to Q over 3
Sorry, but it was
x1 L over e iota.
It was QL times 2L to the power of 2. So
okay, yeah, you're right.
Maybe
so
it's
it is
QL,
the
yes.
power of 3 up here. Thank you. Plus, this is a plus. Plus phi A2, which was equal to x2 times L over 3 e iota, because it was 2L over 6. This is equal to 0. Do you think it is right, or there is any mistake? Please remember that we are saying we are dealing with this, so the rotation associated to the external load, which is clockwise in the node A. When we apply the x1, it is counterclockwise, the node A. You can see it here. And it is clockwise again when we apply x2. Okay? So, right. This is not plus, 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 but I will draw it with the minus in red, minus, and this is minus. Okay, we can, one good rule is to use as positive the reference when where we have the redundant force associated to the rotation that we are considering. In this case, x1 is the one associated with the node A. This term can be positive. all the terms that are coherent, are homogeneous with that one, are positive. All the opposite ones will be negative. So we can write it better. 2 over 3 x1 L over e iota minus x2 L over 3 e iota minus q L to the power of 3 over 4 e iota. This is equal to 0. This is the first compatibility equation. Obviously, iota, iota, iota are common terms and we can get rid of them, simply multiplying both terms times iota. And similarly, we can multiply everything times 3. So we have and divide everything times L. Sorry for the confusion. Now I will write it again. 2x1 minus x2 minus 3 over 4 q L to the power of 2 equal to 0. Please remember that we are dealing with x1 and x2, which are rotations, which are bending moments. So the dimensions are the ones of a force times a length. So here we have q, small q, which is a distributed load, times a length to the power of 2. So the dimensions are right. This is the first compatibility equation. Now, let's see the second compatibility equation. Delta phi c is equal to 0. So we have delta phi c0 plus delta phi c1 plus delta phi c2 equal to 0. Delta phi c1 phi0 was equal to q L to the power of 3 no. 4 iota. Then we have delta phi c1, which is equal to x1 L over 3 iota. Delta phi c2 is equal to x2 L 3 iota. All this stuff is equal to 0. Now let's go back, let's check the signs. We said we want positive rotation that are the ones induced by a positive static unknown applied in the node C. So we are dealing with x2, and so it means that we have a positive rotation on the right hand side in the node C that is clockwise. So if we sum up this term, the other term, and the last term, we can find that they are all positive, but the first one. So it is minus and plus. So again, as before, iota, 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 we can get rid of them. L, L, we can simplify them. Oh, no, 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 wrong. This is not over 3. This was x2L over iota. Then we multiply this times 3 and times 3. So we can write it properly. And we have minus x1 plus 3x2 plus 2 L, no, 3, sorry, 3 Q, L to the power of 2 over 4 iota. This is our second compatibility equation. So if we compute all the stuff, I get rid of the exercise of the computation because it's quite boring, but you should check them out. And we have more interesting things to check. We end up with x1 is equal to how much? 3 over 10 QL to the power of 2. Whereas x2 is obviously equal to 1/2 of that with negative sign. This is the couple of static unknowns which applied on this second structure induce the same displacement, the same deformation, and the same internal forces that characterize the first one, because the structure is different, but we are imposing the same complete equations. So 0 rotation in the node 1 and 0 rotation in the node C. Okay. Okay. So far so good? Now we can just go quite fast and see how to compute the internal forces in this structure, because last week we had no time to do it. If you have any question, please, this is the moment. There is someone who wrote something, maybe, the chat. No. Okay, so we can go on. We have the beam. Yes, yes. With QL applied in the midspan. This is L, and this is L2. And this is x1, which was equal to 3 over 10 And then we have x2. We have to change its direction because we got a minus sign here. And its value is equal to 3/20 2 times L to the power of 2 and nothing else. Okay. So we specify our reactions. We have VD, VC, VA, what's happened? 3/10 QL to the power of 2. QL is here, and then we have 3/20 QL to the power of 2. Again, I will just write the equations I want to draw. Excuse me. So we have equation 1. I'm not computing everything, but it is the equilibrium to the rotation in the node C in the only beam CD, and it is equal to 0. So we take only this beam, we compute the equilibrium with respect to the node C of all the forces. Well, that's trivial. We can find directly the values of the vertical reaction VD, because we have VD. Okay. VD times its lever arm, L, which is positive going counterclockwise with respect to node C, plus the bending moment x2, so 3/20 QL to the power of 2. This is equal to 0, so we can simply find that VD is equal to minus 3/20 QL. So actually is directed downwards. Then equation 2. This is A2. The rotation with respect to the node C of everything has to be equal to 0. Let's go back in the previous slide so we can see all the contributions. We have VD, and we have already found out this value. We don't have this term because it is applied both clockwise and both counterclockwise in the structure. So when we have an internal force, it never appears in the equilibrium of global rotation. And we have VC, which is still unknown, but has 0 lever arm, so it does not appear in the equation. Then we have QL, we have L lever arm, because it is applied in the node B, which is far from the node C, L. And then we have this moment, and we know its value, and finally VA, which is unknown. So the only unknown here is VA. I will not write all the equation because it's quite long and it's not interesting, but the solution is VA. You can check it, just working on your notes. 23/40 QL. Finally, the easiest equilibrium that we can think of, let's come back here. We have found out now VA. The only unknown is VC, which is still unknown, and it's a vertical force. So we can just apply a global equilibrium of vertical forces. So this is a sum of all the forces. This is F, even if it does not seem to be F. Okay, maybe this is better, Fy, because it's in the y direction of all the forces. The result is trivial, and again, I will not write all the equations, but we have Vc equal to 23/40. I will just check it because I don't want to have made any mistake. Just give me 1 second. Maybe. We have QL minus VA minus VD. QL minus 23/40 plus 3/20. Yeah, that's right. We have we can find the resolution just with all the equations also on the notes that Gentile has sent you. Yeah, 23/40. Sorry, but I did this example for the last week, even if I could not do it on class. So I was quite surprised that they ended up to be equal, but they are equal. And so now we can compute the equilibrium equation, the internal forces, pardon. With respect to this beam. Okay, and this will be very simple. But we have seen it not so many times. So we have our structure. We cut this structure at a generic X. Okay. We are starting, originally we start in the node A. So we have, the moment, 3/10 QL to the power of 2. And then we have the vertical reaction, which is 23/40 QL. We have nothing, we cut it. We have to find our unknowns, which are the axial force and X, the shear force, and we consider it positive going downwards, which induces a clockwise rotation in the node, and a bending moment mx. So if we make the sum of all the vertical force, of all the horizontal forces, so we can call it fx, is equal to 0, we directly find that the axial force is equal to 0. Then we have some problems with the blackboard. Now we have the vertical reactions. And we find out that Tx is equal to 23 over 40 to L, because we have Tx going downwards minus 23 to L times 40. Then there is a Q that I lost. So we have Tx minus 23 over 40, la la la, equal to 0. We put 23 over 40 on the other side of the equation, and this is the result. And then the rotation with respect to the node in which we applied the cut. So we find out that mx is equal to minus 3 over 10 to L plus, let's say, yes, plus 23. No, okay, it's too small. I will write it here. Apologies. Minus 3 over 10 to L plus 23 over 40 to L x. And this is power of 2. So the signs are right. So we find that, as usual, as we expect, we have no distributed load applied. So we have a constant shear force, which is always equal to 23 over 40 in every part of this first section of the beam. And since we have a constant shear force, we have a linear bending moment, okay? Because we have only a constant term plus a linear one with x to the power of 1. So the bending moment varies between two minimum and maximum value, which is m, where x is equal to 0, is minus 3 over 10 L to the power of 2. And we find that the value of the bending moment in the node A is exactly equal to the reaction, the external reaction with the opposite sign, and that's what we expect. Whereas the bending moment in the node B, so where x is equal to L, is equal to 11 over 40 QL to the power of 2. So far so good. New page. Now we have to go beyond the node B. We cannot perform the internal forces of node AB in the same equation with the node with the part BC, because we have a discontinuity. Okay, so we have to compute internal forces with different equations on different structures, applying equilibrium equations, obviously, but with a different equation every time we have a discontinuity. And this discontinuity can be both in a geometrical discontinuity, so maybe the structure, the beam, has a change of direction, and we have seen it, I think, last week, but you can find the resolution of that structure in the slides that Gentile sent you. Or it can be a load discontinuity, so maybe we have a distributed load that is not applied on the entire structure, but only on a part of it, or maybe we have some local concentrated load. This is the case. So 23 over 40 to L and 3, come on, 3 over. That's too close. Magnify it, otherwise it will not allow me to write. 3 over 10 QL to the power of 2. Okay, and we have a cut here. Come on. And so we have nx, and we can generically write nx, or maybe we can write nx bc in order to be sure to do not make any mistake. But now I am drawing it this way, just to tell you that you can write all, you can use all these references for the normal one where we have no indication of the beam. Now, we have possibilities. People usually have to find their way. You can just write all the equation with respect to this structure, or start a new structure starting in the node B, where we have the last part. This was the x tilde. So this was x tilde. I have to write it bigger. So you have the possibility or to work on this structure, taking everything with you, so working only on the reactions, or you can restart the structure here. And in this case, you have to explicit the value of internal forces. Okay, let me write it all, and at the end it will be clearer. We just restart the structure in the node B, and I will highlight it here in green. And what do we retain? We compute here all the internal forces, that were the internal forces that we computed here. So we have Nx equal to 0, I didn't write it. Tx is equal to 23 over 40 QL, and M in L is equal to 11 over 40 QL. Okay, and then we have the shear force that was, I don't remember it, 23 over 40. So we have in the node B no horizontal force, because there was no axial force. We have the shear force that we computed previously, 23 over 40 QL. We have the applied load QL going downwards, and then we have the bending moment that we have computed previously, which is, in this case, clockwise, and its value is 11 over 40 QL. And I want to show you that working in this way is much easier, because if we want to compute, we want to write something, okay? If we want to compute the shear force, okay, that's trivial. Fx is equal to x, so nx is again equal to 0. But that was trivial. Then we have the Fy is equal to 0, meaning that x is equal to 23 over 40 QL minus QL. So minus 17 over 40 QL. I would say, let me check. Yes. And the computation of the force here is exactly the same working on this structure or on this structure, because we have QL and 23 over 40 QL. So in the equation, nothing changes. But the equation of equilibrium of the rotation is simpler here, because we have just the contribution of 11 over 40 QL and the QL minus times 6 minus 11 over 40 QL. Is it right? 11 over 40 with positive sign. Okay. So M in the node B. So when x is equal to 0 is 11 over 40 QL. That's what we expected. Whereas M in x equal to L is equal to minus 6 over 40 QL. Okay, to the power of 2. Now I was just checking if the dimensions were right, and I noticed that I forgot the power of 2 to the length. Okay? Otherwise, if we had worked on this previous structure, the equation on this structure, we could compute still easy the M. But in this case, we had to compute M in x tilde equal to L and in x tilde equal to 2L. So the computation is more complex. This is a simple case, okay? Nothing is not that different. But keep it in mind that generally it's easier to compute the internal forces at the beginning or at the end of each part of the structure. And when you start again, you don't consider all the reactions, but only the internal forces that are applied in the node where you're starting from. In this case, node B, and no more node A. Now, the last part, we have two possibilities, again. Or we start from A, so we have the reaction in A, depending moment, 2L, the reaction in B, and then we can cut it, and have x tilde, and we can find n in x tilde, t in x tilde, m x tilde. You can understand that the computation of m, n, and t is not that difficult, but is quite long. You have the other possibility to start from node D. This was B, this is C. Okay, if you start from D, well, that's much easier because we have only the vertical reaction in the node D which was equal to something that we computed before. It was 3/20 to L. Again, x t and bending moment are this. So we can find n is everywhere equal to x to 0. I don't write it anymore because it's trivial. Then we have shear force minus 320 QL equal to 0. So it is equal to 3/20 QL. Okay? And it is constant because we have no load applied. No? And then we have the bending moment. Which is minus 3/20 QL times x. This is x, even if it doesn't seem. So it is linear. M where x is equal to 0, which is the node D. This one is 0. We expect it because in the original structure, we had a hinge in the node D. So we have possibility to rotate. This means that there is no bending moment which prevents any rotation. Whereas in the node C, M in x equal to L, this is L, is equal to minus 3/20 Q L to the power of Q. Notice that it is exactly the value of the bending moment it is, sorry. Okay, 6/40 is obviously 3/20. Okay, so it is the same value that we found in the node C, analyzing the other part of the structure. So that's what we expect, and both of them are equal to, what is it? Okay, this. dx2. Okay? So these are the checks that we have to do. The internal forces are continuous, so they do not vary abruptly during along the structure, unless we have an external load. In this case, we had a vertical force applied in B, whose entity was equal to QL. And we can easily recollect that there is a jump in the shear force is this one. The shear force in the node B belonging to the beam BC is equal to minus 17/40. Whereas the shear force in the node B, but in the beam AB, so right before the application of the load, was equal to 23/40. So there is a discontinuity of the shear force, and only of the shear force, because axial force is still 0, both on the right-hand side and on the left-hand side of the load applied to L. Same is the bending moment, is always 11/40. But the shear force has a discontinuity whose value is exactly the value of the external force that is applied to L. So when we draw, when we compute, and then we draw the plots of the bending moments, and you have the plots of the bending moments in the slides, you can check that there is no discontinuity unless you have an external force applied. Okay, so far so good. We can go on still at a quarter of hour, no more, doing another exercise, starting another exercise, just to see the main features of it. If you have any question, please tell me. Just a couple of seconds. And as I said before, let me check it. Okay, in the Friday afternoon, let's say okay, you have lectures after it, Monday and Wednesday. Okay, I would say Mondays at 5 o'clock in the afternoon, from 5 to 6. I will be on my personal page. If you have any doubts, you can access it and just ask me. Okay, we can see together exercises. If you want, if you even are in Milan and you want to come personally at the department, you are more than welcome.
Professor, I'm sorry about this. Can you please send maybe an email with the link to your personal room, because I have some struggles finding it.
Okay, yeah, sure. You should find me on the page of Politecnico. If you look for Professor Antonello Ruccolo, you should find my personal page with my virtual room. But I can write it in a paper, in a PDF, and upload it on the VVIP page of the course.
Thank you very much.
Of the date. Okay, so far so we can go. Okay, I don't want to solve this example because it's quite long, but it is very interesting. So we have this structure, which is a frame. In Italian, it is a telaio. So it is no more a continuous load, a continuous beam. With a distributed load. Dimensions, as usual, are the same, just not to mess with it. We have already seen how things changes when we have different dimensions. And we have node A, node B, node C, node D. So how many degrees of freedom do we have? Anyone wants to guess? Come on, guys, that's quite easy, I think. Oh, 3. That's right, because we have just one element. So 3 degrees of restraint, 3 degrees of freedom. We have more degrees of restraint. So let's check and let's try to understand how we can downgrade it. Okay, let me just say something. Okay, the problem is obviously in the node B. Okay, everything is converging in the node B. So we can, first of all, allow possibility to rotate. Why the problem is in node B? Because we have the beam AB, which is completely fixed with the node with the beam BC and with the beam BD. So how do we release that constraint? That's trivial. Let's look for it carefully. So first of all, we can allow the possibility to rotate. How can I do that? That's not so easy here. Okay, we can just cut the section here. We don't want actually to cut the section, but to allow a rotation. Okay, so introduce an internal hinge in this part of the structure. Okay, so this is the internal hinge, and then we can explicit the redundant force associated to that. So it is x1, and obviously it will be x1 on the other part. The problem is the structure is still redundant, and we can easily understand it. But how can we go on? We can just allow also possibility to rotate here. Okay, so we introduce a second hinge here. And in this case, we will need, this is the direction, yes, of x2. Okay, so you have to work progressively removing internal restraints. So in this case, it was not enough to reduce only, to downgrade only 1 degree of restraint, but we needed 2 degrees of restraint. So in this case, the structure is statically determined. We can write again the structure. It can be simplified like this. X1 is applied only on the beam AB. Do you agree? Then X1 is also applied, it is here, on the node BC. Okay, because we had this one and we had this one. It is not applied in the beam BD, this one, because we have put also this internal hinge. So there is no transmission of moment from the node BC to BD. Then we have X2. X2 is surely applied on the beam BD. Okay, it is here, this one. But it is also applied here. Similarly to before, since we have this hinge here, this bending moment is only transferred to the beam BD. Sorry, BC. Okay, so this is the schematic of the redundant forces that are identified downgrading the internal restraint in the node B. So we have x1 and x2, which are applied to both node AB, BC, and BD with this schematic. Now, what do we have to say? Obviously, the compatibility equations will need to ensure that we have no possibility to have mutual rotation in the node B. Oh, sorry, I am. Maybe it is better to look at it. So we want to restore the zero mutual rotation in the node B of beam AB with respect to BC, and the mutual rotation of the node BD and with respect to node to the beam BC. So we can write it. Okay, let's start with superposition principle. So we can identify all our terms. Okay, the vertical distributed load Q. The deformed shape will be obviously like this. We have no vertical displacement of the node. Let's give our names. The node B does not move, does not undergo any horizontal displacement because both AB and BC beams are rigid. And since also the column, let's say BD, is rigid, we have that there is no elongation or contraction of the column. So the node B stays here. But we have possibility to have rotation. So we have B in AB is equal to BC in the node B. And it is equal to something that we have seen so far so many times. It is QL over 1, 2, any mistake, 24. I lost it too. Okay. And we have the rotation in the node B associated to beam or column BC is equal to 0. Then, again, superposition principle, we consider a different load, which is no more the external load, but it is x1. So x1 is applied only on these two beams, and so this is the deformation associated. Do we agree?
Sorry, Professor, how come phi b at BC is both equal to 0 and to the QL over 24 EI?
Yeah.
No, but how come it's equal to both? It's impossible to be equal to both, no?
I think it's BD. BD equal to 0.
Oh, sorry, yes. Thank you. Okay. That's right. Guys, do you agree with this? There is maybe something that I am missing. I'll tell you. That is important in this point. But I wanted to notice it after, but we have no time to make all the considerations with the due time. So let's focus on the important thing. In this case, we have again sorry, this is 0, 0, and 0, as usual. P81, sorry. PB1 in AB is x1 times L over 3 iota. And it is equal to this other rotation, which is PB1 BC. Whereas PB1 BD is equal to 0. Oh, come on. Okay. So far, so good? I guess it is. And then the final one. We have just to consider only the influence of x2, and it was here. So the deformation associated is this one. This is B, A, Q, and this is C, B, B, C, Q, and this is B, D. So we have P, A, P, B, Q in the node AB, which is equal to 0, because we have the hinge. Then we have phi B2 in the node BC, which is equal to phi B2 in the node BD, which is equal to, again, x2 L over 3 iota. Okay, because the geometry is the same. So far, so good. Then we can just write the compatibility equation, which state, okay, what did we do? We just released the possibility to rotate in the node B of beam AB with respect to beam BC. So phi B AB minus phi B BC has to be equal to 0. Okay, so when this rotation, this internal rotation will be equal to 0, it means that the continuity on this first part of the beam is restored. Okay, do you agree? Because initially we put this hinge, and then now we are trying to remove it, applying the compatibility equation. So let's go back to our compatibility equation, and this is what we have. Then we have the second one, which states we want to remove this hinge. So we want to say that the rotation in the node B of the beam BD minus the rotation in the node B of the beam BC has to be equal to 0. So we are removing this constraint. So BD minus BC is equal to 0. So before, at the beginning, we remove restraints. And then we restore them, simply applying our compatibility equations. So we can write, and we can do it quickly, our compatibility equations, write them in black. So we have B0 AB plus PB1 AB plus PAB B2 minus PBBC 0 plus B1 plus PB2 B is equal to 0. We substitute all the terms. And we end up with this equation that states, okay, let's be careful about the signs. Let's consider all the positive rotation. What's happening? Sorry. Okay. In this case, we have, when we impose this kind of a compatibility equation, we have to set some reference system. So in this case, all the rotations in the clockwise direction will be positive. Okay. So PB0AB is the QL to the power this one, which is both on this side and on the other side. But in the first side, it is negative because it is counterclockwise, whereas in this side is positive clockwise. So here it appears with the minus q to the power of L to the power of 3, 24 iota plus something minus, and in this case it will be positive 24 iota. Everything 0. Then phi B1 in AB and phi B1 in BC. It was everything here. Phi B1 AB is this one, and in BC it is the same. And again, we have same conventions, same sign, because the first one is negative because it is counterclockwise, whereas the second one is positive. So, and the value was Q x1L over 3. So this is no more a minus, but it is plus, minus x1 L 3 iota. And here it will be positive, x1 L 3 iota. Then we need the second term, which was phi B2 AB and phi B2 in BC. So in AB it is equal to 0, so it does not here, it is equal to 0, whereas the second one is counterclockwise, so clockwise, pardon, so it is positive, x2 times L over 3 iota. So it is plus 0, we can neglect it, plus x2 L over 3 iota. Please notice that we are still using every time the same E and the same iota, because in the assumption originally we are considering a structure which has same material for both the beams and the columns, so the value of E is the same, and also the same section, so the iota is the same. Whereas E and iota were different, we should distinguish between the E and the iota of all the terms, all the elements. So this is the first equation. Then we can write the second equation, which is phi b bd, the rotation in B of beam BD minus the rotation in B of beam BC is equal to 0. We can check all the terms. Now, honestly, it is quite late, so I don't want to go into details. You can find all the passages on the slide. And the thing most important is be careful about the signs. Please don't give them for granted, because it can change a lot your results and lead you to wrong results of the exercise. So far, so good. If you have any question, please, this is the moment. Otherwise, we can have a break. And after the break, you will have the lecture of Professor Gentile. Well, no news, good news.